Welcome to today's lesson. Our topic is mechanical waves.
Is there more than one kind of mechanical wave?
That is a very good question. All of the waves that we see in nature, like stadium waves, sound waves, waves on a guitar string or waves on a pond, are one of two types. What defines the two types of mechanical waves is how the motion of particles in the wave medium compares to the transfer of energy by the wave.
So the reason we care about waves is because they carry energy from one place to another?
Absolutely. Waves travel and take energy with them. The particles that carry the waves will vibrate to transfer the energy along. How the particles vibrate determines what kind of mechanical wave we have. Let's watch a short video that shows both types of mechanical wave. Notice the movement of the slinky coils for the transverse wave. They move up and down while the energy, the peaks, travels from left to right.
I think I get it. The coils in the longitudinal wave look like they're being squeezed together and then spreading apart.
That is an excellent observation. The coils in the longitudinal wave vibrate left and right, and the energy also travels left to right. Let's summarize what we've learned. In transverse waves, like a stadium wave or ripples on a pond, the particles vibrate up and down while the energy travels left to right. The two directions are perpendicular.
But, for longitudinal waves, like sound waves, the particles vibrate left and right and the energy travels left to right. They're in the same direction.
Now let's look at different ways we can describe waves. All of the wave characteristics will apply to both types of mechanical waves. This graph shows the motion of a single particle as it moves. The vertical axis shows the displacement of the particle and the horizontal axis shows time. The graph shows 6 waves or 6 cycles of particle motion.
So one cycle or wave is what it takes for the particle to come back to its starting position?
Exactly. We can use this graph to determine how much time it takes to complete one cycle. You will remember from circular motion that this is called the period of motion. This graph shows 6 cycles and it takes 30 seconds to complete them. To find the period we want the time for one cycle, so we divide the time by the number of cycles.
So, 30 seconds divided by 6 cycles gives us 5 seconds per cycle. This means the period is 5 seconds.
To find the frequency, everything is flipped. So frequency is the number of cycles divided by the time it took.
Is there anything else we can find out by looking at this graph?
Yes, there is. We also want to know how tall the wave is. The zero displacement line represents the equilibrium or rest position of the particles.
The maximum displacement of a particle from its rest position is called the amplitude of the wave.
Notice that the particle moves the same amount, 2 mm in this example, from the equilibrium position in either direction. There is a second graph that we can make. It shows a freeze-frame picture of all of the particles in the wave at the same time.
Since the vertical axis is still particle displacement, we can use this graph to find the amplitude just like we did with the first graph.
But the horizontal axis is no longer time. It now shows the position of a particle in the wave medium. We still see wave cycles in the graph. We can still measure the length of a wave cycle. But now it will tell us how long the wave is. We call this wavelength.
In this example, the wavelength is 5 centimeters.
We use the Greek letter lambda, which is still an L, to represent wavelength. Here is what it looks like. We can define the speed of a wave just like any other speed. We need a wave distance, we'll use the wavelength, and a wave time, we'll use the period. Speed equals distance over time, so for a wave, speed equals wavelength divided by period.
But, since frequency is 1 divided by the period, We can substitute in this equation to get wave speed equals frequency times wavelength.